Hello, and welcome to section 11.11 on applications of Taylor polynomials. In this section, we will discuss the main use of Taylor polynomials, which is to approximate functions. In this section, we suppose a function f is the sum of its Taylor series at a. F of x equals the sum, k equals 0 to infinity, of the kth derivative of f at a divided by k factorial times x minus a to the k. Recall that the nth partial sum of this series, Tn of x, is called a Taylor polynomial. Tn of x equals the sum, k equals 0 to n, of the kth derivative of f at a divided by k factorial times x minus a to the k. As f is the sum of its Taylor series, it follows that Tn of x gets closer to f of x as n goes to infinity. Thus, Tn of x is approximately f of x, and this approximation gets better as n gets large. Notice that when n equals 1, we have that T1 of x equals f of a plus f prime of a times x minus a. You might recognize this as the equation of the tangent line to the graph f of x at the point a, f of a. Recall this is just the linearization of f of x at x equal to a, and this tangent line approximates f of x quite well for x values close to x equal to a. This is the idea behind using Taylor polynomials to approximate functions. Higher order Taylor polynomials, Tn of x, give better approximations to the functions than the linearization does. The advantage of approximating a complicated function by polynomials is that polynomials are well understood and easy to compute. The following figure shows the graphs of several Taylor polynomials which are approximating sine of x and cosine of x at x equal to 0. For another example, here are some approximations of the function f of x equal to the natural log of x plus 1 about x equal to 0. Let's look at an example. The third degree Taylor polynomial of f of x equal to sine of x at x equal to a is t3 of x equals sine of a plus cosine of a times x minus a minus sine of a divided by 2 times x minus a squared minus cosine of a divided by 3 factorial times x minus a to the third. For a equal to 0, we have that sine of 0 equals 0 and cosine of 0 equals 1. Hence, t3 of x equals x minus x cubed divided by 6. So for example, the value x equal to 0.1 is close to a equals 0, and sine of 0.1 is approximately t3 of 0.1, which equals 0.1 minus 0.1 to the third divided by 6, which equals 0.099833333. The actual value, sine of 0.1, is 0.099833416, which agrees with t3 of 0.1 up to 6 decimal places. We can also explicitly determine how good our approximation is as well. Recall the remainder, Rn of x, equals f of x minus Tn of x. If we obtain an upper bound for Rn of x, then we can understand how accurate our approximation is. We can also determine how large of n we need to minimize the error when approximating f of x by Tn of x. Fortunately, we do have an upper bound for the absolute value of Rn of x, thanks to Taylor's inequality. If the n plus 1 derivative of x is less than or equal to m, then the absolute value of Rn of x is less than or equal to m divided by n plus 1 factorial times the absolute value of x minus a to the n plus 1. Thus, if we can figure out what m is, then we can figure out how good our approximation is. For example, let's approximate f of x equal to the third root of x by t2 of x when x equals 8. How accurate is this approximation when 7 is less than or equal to x is less than or equal to 9? We first compute t2 of x, and to do this, we need to compute up to the second derivative. F of x equals x to the 1/3, and f prime of x equals 1/3 times x to the negative 2/3. And thus, f double prime of x equals negative 2/9 x to the negative 5/3. Evaluating at a equals 8, we have that f of 8 equals 2, f prime of 8 equals 1/12, and f double prime of 8 equals negative 1 over 144. Then t2 of x, which equals f of 8 plus f prime of 8 times x minus 8 plus f double prime of 8 divided by 2 times x minus 8 squared equals 2 plus 1/12 times x minus 8 minus 1 divided by 288 times x minus 8 squared. Thus t2 approximates the third root of x for values of x close to a equal to 8. So now, how accurate is this approximation when 7 is less than or equal to x is less than or equal to 9? By Taylor's inequality, we have that the absolute value of r2 of x is less than or equal to m divided by 3 factorial times the absolute value of x minus 8 to the third, where the third derivative equals 10/27 times x to the negative 8/3 is less than or equal to m. All that remains is to determine a suitable m. Note that 7 is less than or equal to x is less than or equal to 9, and in particular, x is greater than or equal to 7. So x to the 8/3 is greater than or equal to 7 to the 8/3, and thus x to the negative 8/3 is less than or equal to 7 to the negative 8/3. Therefore, the third derivative at x equals 10/27 times x to the negative 8/3, which is less than or equal to 10/27 times 7 to the negative 8/3, which is less than 0.0021. So if we choose m equal to 0.0021, we get that the absolute value of r2 of x is less than or equal to m divided by 3 factorial times the absolute value of x minus 8 to the third, which equals 0.0021 divided by 6 times the absolute value of x minus 8 to the third, which is less than or equal to 0.0021 divided by 6 times the absolute value of 7 minus 8 to the third, which equals 0.0021 divided by 6, which equals 0.00035. Therefore, the error of the approximation t2, which is approximately the third root of x, for 7 less than or equal to x less than or equal to 9, is at most 0.00035.